Hi folks! This is the first video of the semester for Advanced Organic. Today's video is going to be talking about bonding, and starting much in the same way that we started Intro Organic Chemistry, I'll be talking about atomic orbitals, VSEPR, and hybridization. Hopefully most of this is going to look like review. So we obtain the shapes and concept of atomic orbitals from quantum mechanics. We will not be getting into the details, but I do want you to know about the s and p orbitals. So s orbitals are spherically symmetric, and we have 3 p orbitals that are degenerate or equal in energy. These are oriented along the x, y, and z axes. The phasing of p orbitals, or essentially when I draw them, their color or shading, is a common misconception. So here I've drawn a p orbital, and rather than using 2 different colors for the different lobes, I'm using an unshaded lobe on top and a shaded lobe on the bottom. So this color or shading is just a mathematical construct. So one of the sides, here unshaded, I'm showing as the positive function for the quantum mechanical solution to the atomic orbital, and I'm designating the shaded side as a function that is negative. As I said, this is just based on a mathematical description of the orbital. And really importantly, you're equally likely to find an electron in either lobe of the p orbital. The nucleus of the atom is located in the middle of the p orbital, and the nucleus lies in what's known as a nodal plane. This plane separates the 2 lobes of the p orbital, meaning it separates the positive and negative regions of the mathematical function. You have a 0 probability of finding an electron in this nodal plane, which for the p orbital means you have a 0 probability of finding the electron at the nucleus. Restated, this means that there is no electron density at the nucleus for a p orbital. We'll use the concept of hybridization frequently throughout the course to describe bonding of organic molecules. And we get these hybrid orbitals by mixing atomic orbitals, essentially adding and subtracting the atomic orbitals to get these hybrid ones. So to start out, let's consider our atomic orbitals. We'll just consider the s orbital and the 3 p orbitals. The s orbital is always going to be lower in energy than the 3 degenerate p orbitals. Now let's consider, what if we mixed the s orbital with just the py orbital? This is our p orbital oriented horizontally. When we mix these 2 orbitals together, we end up with 2 mixed or hybrid orbitals coming out. These are called sp hybrid orbitals, and they are oriented along the y-axis because we made them using the py orbital. Notice that each of these sp hybrid orbitals has 1 large lobe and 1 smaller lobe. This hybridizing accounts for the s and the py orbitals that we put in, but we also have to worry about the orbitals that we did not mix together. These are the px and pz orbitals, and they have the same energy as the atomic orbitals because they haven't been mixed in any way. Notice that the sp hybrid orbitals are higher in energy than the starting s orbital. This type of mixing gives us sp hybridization. We mix together two of our orbitals to get two sp hybrid orbitals, and we have two remaining unhybridized p orbitals. Now I want you to consider, going back to our initial atomic orbitals, what if I mixed the s orbital with the py and pz orbitals? So mixing 3 orbitals instead of 2. When I mix these 3 orbitals together, I will get out 3 hybrid orbitals. These are called sp2 hybridized because they're made from 1 s orbital and 2 p orbitals. And they have 1 large lobe, 1 small lobe each, and they're oriented 120 degrees apart in a plane. Notice that as we mixed in more p orbitals in this case, our hybrid orbitals ended up higher in energy compared to our sp hybrids. The more p orbitals of higher energy you mix in, the higher the hybrid energy orbital level will get. So we've accounted for 3 of our orbitals. What about our final px orbital? Well, because we haven't mixed it with anything, it has the same energy as the atomic orbital because it's unhybridized. So overall, to get sp2 hybridization, you mix together an s and 2 of your p orbitals to get out 3 sp2 hybrid orbitals, and you'll have 1 unhybridized p orbital remaining. Our last scenario is, what if we started yet again, going back to our original atomic orbitals? What if we mixed all 4 of these orbitals together? Or mixing s with px, py, and pz. When we mix 4 orbitals together, we'll get out 4 orbitals. Each of the orbitals we get out will be sp3 hybridized. It gets this name because we've mixed 1 s orbital with 3 p orbitals. Here again, our hybrid orbitals have 1 larger lobe and 1 smaller lobe. And in this case, I've tried to draw it, but I didn't do too good of a job. I tried to draw that they're sort of oriented 109.5 degrees apart, sort of pointing out in a tetrahedral way. Notice that when we went from sp2 to sp3, our hybrid orbital energy went even higher because we mixed in even more higher energy p orbitals. So our final scenario for an atom with sp3 hybridization is that you'll end up with 4 sp3 hybrid orbitals and you'll have no remaining unhybridized orbitals. I'll show how I would draw what I would call a hybrid orbital diagram for ethane, ethylene, and acetylene. These will be our sp3, sp2, and sp hybridization examples. In the case of ethane, where each carbon is sp3 hybridized, it's going to use its 4 sp3 hybrid orbitals to form 2 different types of bonds. Each carbon will form 3 different bonds to hydrogens, and it'll use its 4th sp3 orbital to form a carbon-carbon sigma bond. Hydrogen only uses its s orbital in bonding, so that is what it will always contribute. For ethylene, let's look first at the sigma bonds. So the carbon is sp2 hybridized, and it's going to use its 3 sp2 hybrid orbitals to form sigma bonds. 2 of them will be to hydrogens, and one will be to form the carbon-carbon single bond. The unhybridized p orbital from each sp2 hybridized carbon will go to form a pi bond, where the pi bond is our side-to-side overlap of our two unhybridized p orbitals. If you remember from intro OChem, this pi bond has a way of restricting the rotation about the carbon-carbon bond. And for acetylene, let's start out with our sigma bond framework. Each carbon is sp hybridized, and it uses its sp hybrid orbitals to form one bond to hydrogen and one sigma bond to the other carbon. Then each carbon has two remaining unhybridized p orbitals. The p orbitals on each carbon that are oriented in the same direction make up one of the pi bonds. And then orthogonal to the first pi bond, or perpendicular to it, we get side-to-side overlap of our second p orbital on each carbon to make the second pi bond. One thing that's important, but that I forgot to mention earlier, is that each of the carbon hybrid orbitals, which I'm showing in pink, going to form the bond to carbon or hydrogen, in these cases I'm only drawing the large lobe of the hybrid orbital. Just be aware that on the opposite side of the carbon from this larger lobe is a smaller lobe. I just don't typically draw this because it makes my diagram cluttered. For organic chemistry, we'll often use VSEPR to quickly predict the three-dimensional geometry of a molecule. This is a good first approximation of bond angles. And in the chart that I'll show you below, I'm going to use the term electron groups that are around an atom. And an electron group could be a lone pair, a single bond, a double bond, or a triple bond. So if you have two electron groups around an atom, you're going to have a linear geometry about that atom. The bond angle will be approximately 180 degrees, and this is what we'll see for sp hybridized atoms. If instead you have three electron groups around an atom, you'll have a geometry about that atom of trigonal planar. The bond angles will be around 120 degrees, and you're going to see this in cases where you have sp2 hybridization. And for organic chemistry, the last example we'll really look at is when you have four electron groups. You'll have a geometry about your atom of tetrahedral. Bond angles will be about 109.5, and you'll see this for sp3 hybridization. So I'll show three examples to begin. The first of these is hydrogen cyanide, a really toxic gas. So let's think about the geometry about the carbon. I'd say there are two electron groups around this carbon. One of them being the nitrogen that it's triply bonded to, and the other one being the hydrogen. So we have two electron groups. We'll predict that it's going to be linear with bond angles of about 180 degrees. Next, let's consider a tetrasubstituted alkene, and we'll have to think about the geometry and angles about each carbon. Let's focus specifically on this bottom carbon of the alkene. So I'd say there are three electron groups around this carbon of the alkene. Two of them are methyl groups, and the third is the carbon that it's doubly bound to. So I have three electron groups. I'd predict trigonal planar geometry and bond angles of 120 degrees, And this corresponds to sp2 hybridization. And then, of course, you have something like an alkane, for example, in this case, ethane. If it's been a while since you've thought about organic chemistry, remember that each carbon that is sp3 hybridized can be drawn with two bonds that are lines, one wedge, and one dash. So if we take this carbon on the left, I'd say there are 4 electron groups around it. 3 of them are hydrogens. The 4th one is the other carbon. And since I have 4 electron groups, I'd predict a geometry of tetrahedral with bond angles of about 109.5. I want to specifically highlight carbocations and carbanions as our charged carbon species that we'll see pretty often. Here's an example of the simplest carbocation, the methyl carbocation. Notice that this carbon has 3 electron groups around it, the 3 hydrogens. I would predict that this carbocation would have trigonal planar geometry. In the case of the carbanion, in this case methyl anion, I have instead 4 electron groups. 3 of them the bonds to hydrogens, and the 4th one the lone pair on carbon. This would give me a tetrahedral electron geometry, but because one of those 4 groups is a lone pair, I'd describe the geometry in terms of the bonds to be trigonal pyramidal. The bond angles that I've given so far are sort of the ideal scenarios, not thinking about steric or electronic effects. I want to show you some examples of sp3 hybridized molecules that have deviations from perfect 109.5 degree angles. First, let's consider this alkane, where I have a central carbon with 3 methyl groups attached to it. The central carbon has sp3 hybridization, so we would expect an ideal bond angle of 109.5 degrees, but if you actually measure the angle from carbon to the central carbon to another methyl carbon, you get an angle of 110.6 degrees. So we have a deviation that makes the bond angle between the methyl groups larger. We can rationalize this greater bond angle as being due to steric interactions. So compared to the methyl groups, the hydrogen on the top of the molecule is small, and I have steric repulsion between each of the methyl groups. This is going to push the methyl group slightly up toward the smaller hydrogen, and as I push these carbon methyls up, my bond angle increases slightly. An opposite effect, where my bond angle is smaller than the ideal one, shows up in ammonia. So in this case, the bond angle between the hydrogen, nitrogen, and hydrogen is 107 degrees. What this suggests is that the lone pair is pushing the hydrogens away, and as the hydrogens get further away from the lone pair, they get closer to each other, making the bond angle smaller. This effect is even more extreme when you get to a water molecule which has 2 lone pairs. These oxygen 2 lone pairs push the hydrogens down closer to each other, giving us a bond angle of 104.5 degrees, so even more contracted than in the ammonia example. What these smaller bond angles suggest is that the lone pair is behaving as if it's larger than the bonds to hydrogen. It would be more complicated to predict in cases where you had substituents other than hydrogen as well as a lone pair, because you could have sort of competing effects. But because hydrogen is so small, you can get these contracted angles. The last thing I want to mention is that hybridization, and therefore geometry, can depend on whether or not there's resonance. So I'll define a delocalized lone pair as a lone pair that is participating in resonance, and typically this is because it'll be adjacent to a pi bond. So for example, let's consider an amide, where I have a nitrogen with a lone pair adjacent to a carbonyl. To draw a second resonance structure, I'm going to bring down the nitrogen lone pair to form a pi bond, and break the carbon-oxygen pi bond to make a new lone pair on oxygen. This will give me a resonance structure where I have a carbon-nitrogen pi bond, a carbon-oxygen single bond, and I'll have positive charge on nitrogen, negative charge on oxygen. So the critical thing is that for a lone pair to participate in resonance, it needs to be in an unhybridized p orbital. So you would initially look at this nitrogen and think it has 4 electron groups around it, 2 bonds to hydrogens, a bond to carbon, and a lone pair, and you would initially think that it should be sp3 hybridized. In reality, nitrogen's lone pair needs to occupy an unhybridized p orbital so that it can overlap with the pi bond between carbon and oxygen. This is what gives us our delocalization or resonance. So this means, in the case of the amide, the nitrogen has to be sp2 hybridized so that it has an unhybridized p orbital that can be delocalized or participate in resonance. This makes the nitrogen trigonal planar. Be a bit careful with how I've drawn this lone pair in the p orbital. As I mentioned earlier, that lone pair is, in reality, equally likely to be occupying the top and bottom lobes of the p orbital, but I sort of have to draw it in one of the lobes, and it's easier to just draw it in the unshaded lobe. Alright, so overall, I've tried to review concepts of atomic orbitals, hybridization, geometry, and how resonance can affect hybridization and geometry. That's it for this video. I'll see you in class.